Hi there. We're going to talk today in this video about the problem of optical illusions in the Earth-shape debate. What I'm going to try to do here is explain some basic principles that are things that are not strictly theory that we can test here on Earth and see what we can deduce from that. You can see I've got here a lens that I've shown this diagram before that shows how light behaves in a lens. Okay, I'm going to have that up for a little bit and then I'll switch to a different picture. But first, we need to define what a mirage is. So a mirage is a phenomenon where differences in air density, usually due to temperature, cause an object to appear away from its actual physical location. And it's often also distorted or inverted as well. And sometimes even it will exhibit multiple copies of itself like a kaleidoscope because it will be, showed 5 or 6 copies of the actual image. That's just how light works. If you have that many different lenses of different densities, that's what you'll see. And it's an illusion. So, of course, we're all most familiar with the thing that you see on a hot day when you see the illusion of a small pond of water up the road ahead, really far ahead, usually on a very hot day. Okay, that's a form of mirage. Mirages in general are the result of the refraction or bending of light. And it's really not accurate to say bending because light is not like a plastic tube that you can bend. It's something that, wave, in my opinion, not a particle or photon, but a wave that travels in a certain direction, and it is always going to go straight until it runs into something that deflects it. It's really more accurate to say that it's a deflection of light. So that's what we mean by refraction. It's being bounced in a different direction. It's being deflected to one angle or another from where it was going, and it goes in another straight line. Okay, you've all seen that in a picture of like a prism that will take sunlight and break it up into different densities and thus different speeds and thus different colors of light. And it will do so on the basis of, the shape of the lens and all that. So what happens in nature is that a mirage will happen when there's a refraction of light through a non-uniform medium. That is to say, something that isn't necessarily, it's not homogeneous. It's not all the same stuff that it's going through, whether it's, air when we're talking about visual sight usually. Sometimes you can see through water as well, but usually air. And this happens, you see a mirage when the air near the Earth's surface, whether it's land or sea, is a significantly different temperature than air higher up. Those are the conditions for a mirage. Warm air is less dense than cold air, and as with anything else acting like a lens, like we see here on the screen, light will refract or bend or deflect toward the thickest part of the change in density. Okay, some people say light bends up or down at the horizon. No, it bends toward the thickest part of a change in density. You can see on the lens here that it's thinnest in the middle, and that's called the principal axis, where light goes through without being deflected in its path. So you won't have distortion. But light that's coming at a different point where it's the thickness goes in that direction, the light will bend that way. And the result is that the object, if you're looking at it from this point, looking back at the object, your eye will assume it's going in a straight line and put the object lower than it actually is. That's how optical illusions happen a lot of times. It's not the only way, but it is concerning mirages. Okay, so what we have is air levels or layers acting like different thicknesses of lenses. That's the idea I'm trying to get across here. And warm air, because it's the molecules of air have more motion, they're less dense, and so they have less pressure, and they're not the thickest part of the lens, they're the thinnest part. Okay, so that means that cold air is thicker, it's more dense. So light will refract or bend or deflect toward the thickest part of that change in density. But even in those conditions, the optical illusion of a mirage is only seen if the angle of view is relatively long and shallow. That is, when you look off in the distance, you see the mirage of water on the ground when there's no water there, because it's such a long distance. It's a low angle of view. Okay, a very long, skinny triangle, basically. So now let's look at the different types of mirages. We have a superior mirage on the left, an inferior mirage on the right. Superior means above where it's supposed to be. Inferior means below where it's supposed to be. Okay, and they tell you here, look, if the light is being bent downward, regardless of whether you understand why, if the light is being bent downward toward you, that will result in a superior mirage. Conversely, if the light is being bent up to your eyesight, that will result in an inferior mirage. Okay, so those are the two main types. And the illusion of water on the ground that I mentioned earlier on a hot day is an inferior mirage. It appears below, and it's a reflection of the sky, actually. And it shimmers because of the heat waves, and that's why it looks like water. Okay? Now, the opposite kind, the superior mirage, is you might have heard of these ghost ships, so-called, that seem to float above the water. They're not even touching the water. That's why it looks off in the distance. And that is what they call a superior mirage, because it's way higher than it should be. The most extreme example of a superior mirage is called a looming mirage. I've heard people throw this term looming around, and they don't really precisely define it. I'm not sure if they always understand what it means. It's simply a more extreme example of a superior mirage. Okay, and if for an extreme example, you need extreme conditions. You can't ignore the conditions or the length to the objective, the thing you're pointing at and looking at that is being miraged. Okay, so that's what a looming mirage is. It's an extreme, rare condition, superior mirage. Now, since light bends toward the denser air, it will always bend from hot to cold. So, if layers of air cause light to bend down toward you, like I said, the mirage will be superior, and then if it bends up, it's inferior. So we see inferior mirages when the surface is very much warmer than the air above it. And we see superior mirages when the cold and hot zones are reversed. That is to say that the order of layers from ground up is reversed. Okay, superior mirages are most likely to occur over ice or water, especially the ocean, because the ocean is like what they call a giant heat sink. A heat sink is a fluid medium, such as air or water, that dissipates heat. You have different kinds of, it isn't always a fluid. For example, in the microprocessor on the motherboard in your computer, you have a heat sink and also probably a fan. And its purpose, those fins, those metal fins all around the processor, those are heat sinks. And their purpose is to keep the processor from overheating by wicking away the heat from the processor as it produces it. It gets it away faster than the processor can itself. Okay. Now, in nature, the oceans are heat sinks. Okay. So it's getting rid of heat, but it's also absorbing it from one place and putting it out into a colder place. So that's the way convection happens. Warm always goes to cold. And the oceans tend to be colder than the air because that's how the physics works of a heat sink. And in both the cases of either kind of mirage, the image is usually also somewhat distorted. How much distorted depends on the conditions. And that's because the different air densities are not exactly the same throughout the field of view. It isn't a nice, neat thing like this lens I showed you. Let me put that back up. Like if you grind a lens in that shape, you can predict the outcome every time. But nature is not a very nicely ground lens. These air layers can fluctuate in real time. That is from moment to moment. That's why you get shimmering. That's why you get wavy looking stuff. Okay. So the densities in nature are not going to be uniform, and they're not going to stand still for you. So that's why you're going to get usually distortion of some kind. And like I said, I mentioned about the kaleidoscope phenomenon, where you get multiple copies, multiple mirages of one image, of one object, I mean. That's because these layers of air that you can see in the little, the top of that illustration there with the blue, different shades of blue, those are different densities, that these layers can be stacked up. And that's how you can get more than one image, or a blurry or wavy or distorted image. It can also shrink or stretch the image. It can make a building look taller or shorter, wider or skinnier. It just depends on the conditions, which are variable all over the place. So, but the question I'm getting at here is the problem really is that some mirages are pretty obvious, but others make us wonder whether we're looking at a real object or the mirage of it, or any mirage at all. For example, if we see an object very far away, such that it should be hidden by the alleged curvature of the Earth, can mainstream science declare that it must be a mirage? I don't think they can logically do that, or scientifically. Or can we say for certain that it's not a mirage on the other extreme, and the Earth either has no curvature or is much larger than we're told? We can at least say that a distant object behind the alleged mirage will not loom in sync with it, since the physics of light will bend at a much different angle. That is to say, going back to this lens again, you see that all the light is parallel coming into the lens, but it's going to wind up in very different places depending on where it hit. And so the problem with mirages at a great distance, especially if there's something behind them, like a distant mountain. So you've got a building and way behind that is a mountain. If you know that, you can go and check yourself the distance between the mountain and the building, and then you go far away and look at it, and you don't know, by the curvature calculation, you shouldn't see the building. You can know whether or not you're seeing a mirage by how it relates to the mountain behind it, because they will not loom or mirage at the same rate because of how lenses work. Okay, so we know how light behaves in different media, but we also know that if we are looking at something that we think is a mirage, we can compare other things around it at different distances to see whether it keeps the same proportions. If it doesn't, it's probably a mirage. But if the background stuff, the stuff around it doesn't change, but only the object, it's probably not a mirage. Probably. As a general principle, we have to remember that just because something is possible doesn't mean it's a fact. And just because one explanation may be plausible doesn't mean we don't need to consider any other explanations. This is why the scientific method requires a theory to be falsifiable, meaning we must devise experiments to try and break the theory and rule out other theories. That's how you falsify a theory. That's what makes a theory scientific, if there's a way to falsify it and a way to rule out competing theories. That's rarely done. So in the Earth-shaped debate, errors are being made by both sides because they don't apply the scientific method properly, or they engage in logical fallacies. The only real way to actually observe Earth shape, given the fact that both sides have a plausible deniability factor because of perspective or mirages or whatever, they have plausible deniability. The only way to solve this is one of two ways. One is to get so far from the Earth that you can see the whole thing at once, not by stitching images together, but by seeing it all in one shot, which may or may not even be possible, depends on who you want to believe, but that's not something the average person can check. So the other way is to compare a tangent line and a level line. And this gets into what was described, I think, at least a year ago as the force the line. So let me just briefly explain what that is. And you can see I got the words right on here. In a force the line experiment, a post this is the post, is set precisely vertical to the Earth's surface. That is to say, it is in line with the radius of the circle. Flat circle, ball, doesn't matter. It's a circular object, whether it has 2 or 3 dimensions, it has a radius. You go from the center to the edge, any edge, okay? That's a radius. So you put a post along the radius, that is to say, a right angle to the surface, okay? From there, you put out beams. Beams are attached one above the other. The beam following the tangent, that's the green line, is kept at a right angle to this base post. Okay, right angle the whole way, right angle. That's a tangent line. That's what a tangent does. I understand it's off the surface a little bit, but I'm doing this to illustrate a tangent line. It doesn't have to be right on the surface when you're just making sure it's a right angle. That's the point. The other follows level as indicated by a spirit level. Okay, so instead of measuring an angle with something that we're absolutely have measured, like a construction person's device or a carpenter's device, where they check, they have a right angle that they check things with to check corners. It's really important in building. That's the tangent line measurement, but the level will be wherever, if you have a bubble level or spirit level. Okay, if Earth is spherical, the top level beam will eventually run into the tangent beam, because level is defined by keeping the same distance all around the circumference, whereas the tangent is strictly a right angle from a point. And so this level line will eventually curve down into the tangent line, and they will meet. That's why you build a physical structure. It doesn't have anything to do with optics. You eliminate all the plausible deniability as long as you are very precise in right angles and levels. That's all you have to do. That's something people can do on the surface of the Earth. You don't have to be far away. You don't need a telescope, a camera. You don't need any of that stuff. So all you have is a physical object. The problem is getting a long enough length, but it can be done at least enough to show that that level line is bending toward the tangent line. That is to say, the distance between them is shrinking as you go along. Throw away the calculators, just measure it. Okay, that will prove Earth shape, because you can't even just go by the surface of the Earth. You're like, why do I need the level? I already have that with the surface of the Earth. That's because the surface of the Earth is bumpy. And even if you have a very long flat surface, such as the Salt Flats or whatever, I can't remember the name of that place, I think is in South America, way high up in the mountains. It's the biggest, flattest area. I'm sure you've seen pictures of it. But someone is going to always say it's not a long enough length. So you build this structure, I don't care where, as long as you can get enough distance to satisfy both sides of the debate. Even the concave Earth theory, all you'd have to do is put that tangent above and put the level below, because if it's level and the surface curves up, all you do is flip this level a mirror image, so it's like a smiley face instead of a frown, and put it below here. Again, the level line will run into the tangent line. So as long as you have this base post absolutely in line with the radius of the circle, okay, at a right angle to the surface, and you build everything out from there, you will have the answer to the question of Earth shape without optics, without any excuses, and with both sides overseeing the construction of this thing, so nobody says anybody cheated. And then you simply measure it, the distance between these two lines. I don't know of a better way to answer that question. Okay, now I'm going to take a brief look at the chat and then go into one more section here. It is complicated with optics and physics and calculations and all that, but what I'm trying to do is simplify it as much as is possible. That's the sort of thing I do. I am the analytical sort, and I tried to sit back. My purpose in doing this hangout was to sit back and summarize what I can see watching debates on the issue, because people are talking past each other and both sides are making mistakes. Okay, and this is the only way I can think of to settle it. And the one person who had a serious run at building such a device, an engineer, suddenly disappeared. So we need more people doing this, people who aren't going to lose their job or their family if they actually carry this out. And we have to also consider the likelihood of sabotage or worse. So it's a big deal, but I think it's the only way this is ever going to be settled. Okay, the sun angles movement thing mentioned in the chat. I do have a video called Challenging Standard Cosmology, the Sun. It takes a while, but I do have pictures, so that's my best shot at trying to illustrate that issue and how the sun's four motions can be explained. Can be, but again, as I said earlier, that doesn't prove anything. I would have to rule out other theories, and really the best way to test this would be if, you could model it by getting that shape of a lens and rolling a ball across the top and photographing it from a couple angles. But that still wouldn't absolutely prove. It would just say it's possible. That's all it would do. But this kind of an experiment, the force to line, would absolutely answer the Earth-shaped question as long as you can extend the lines physically. Okay, let's check out the chat some more. Law of entropy. Yes, things run down. That's a really different issue. Just heard Chicago 50 miles out, horizon buildings can be seen when should not be able to. Here again, seen is the problem. There is plausible deniability, even though I don't think, the mirage argument is a strong one for the Earth being a certain size and shape. People can decide what they want about that. But the point is, you need a physical straight tangent line compared to a level line, and just measure it. First law of thermodynamics states that heat is a form of energy, and it's wasted energy actually usually. And thermodynamic processes are therefore subject to the principle of conservation of energy. Yes, and they talk in physics classes about heat death of the universe eventually. Because the matter in the universe will have spent all its energy, and so it will no longer be able to do anything. That's what that's about. Anyway, yeah, energy goes to heat, its lowest form, I guess, and then eventually the molecules don't even move anymore. Let's see. Offended an enthusiast of astronomy last night regarding word versus millions of years age and carbon dating. There's an excellent site called Science Against Evolution. I think it's .info. Science Against Evolution, all one word, .info. That does an awesome job of just comparing science with the theory of evolution and blasting all these dating methods and everything out of the water. Without, the only time the guy ever cites scripture, even though he's a Christian, the only time he ever uses it if somebody else brings it up. That's what I try to do in any conversations. I wait for somebody else to bring it up. Then they can't complain that Christians are always pushing your ideas, because we are allowed to defend ourselves. If somebody says something against what we believe, we're allowed to answer it. It's only fair. I don't accept double standards. Let's see. Yeah, being academic is important. It just, depends on the situation. But anyway, Hawaii volcano is not conserving heat. No, it's really wasting it right now. All right. Well, let me go on to the last section that I wanted to cover here. I'm hoping I've illustrated the problem of using optics to prove anything, and the fact that nature's optics are not uniform or consistent or set in stone. They will change rapidly during your viewing of something. So the force to line is the solution that would settle the debate as much as it can be settled. Now, you see here, I've got another model of Earth. And I showed a radius line here. I was talking about that earlier from this. This is the center. This is only a half circle. So this is the center. This line, this radius goes up to the edge. Okay. Any direction doesn't matter. It goes out like spokes on a bicycle wheel. Every spoke on a bicycle wheel is pretty much a radius. Okay. A diameter would be connecting the radius all the way across. It's all the way across the circle is the diameter. Circumference is the line around it. Radius is half a diameter. So a tangent is a right angle to a radius, okay? Just in, visual terms here, we've got a line from the center to the edge. Perpendicular to that is a tangent line. When you look at the horizon, you are looking at a tangent, not a level. You can't see around corners without the lensing. And then they will say, well, we have a curved atmosphere. Well, that is the question being asked. You can't use circular reasoning, pun intended, but that's a logical fallacy. So you can't presume that the atmosphere is bent, and this is why you see, why things appear to be curved. It's begging the question. But also you can see off to the right on this red triangle looking at this building hidden by the horizon, because the horizon is the tangent line. As soon as the Earth in this model curves away, it curves down always in every direction. It's hiding the building because it's gone around a curve and you can't see around it because you see in straight lines. Remember that lens? I think I can bring that up real quick. You see in straight lines, but the lines are deflected by lensing, okay? So when people talk about a hump or bulge that should be between you and a building, they're talking about the fact that this distance, keep in mind, it's the distance of an arc, not the straight line. Here's the straight line on the bottom and top. That's the height of this object. You have a straight line to the bottom, straight line to the top. That's your angle of view, but it's being hidden by this arc section, because if the Earth is that shape, then this shape is going to hide the object from you because the object is stuck to the edge by gravity, or however you want to pronounce that. So when we say we should not be able to see something, we're saying it's at such a distance away that curvature takes the building down and away from us to the point where our straight line of sight cannot even see the bottom anymore, or at least can't see the whole thing. Okay, like in this green one here, you see part of it because it's not as far away. It's not as far down the arc. But it should be leaning away from you. And I think a good experiment would be if you had a very large building, or at least a very tall one, a tall tower with slats or louvers in it that point like 45 degrees down, such that you can't see into the building or through the building while you're looking straight at it. But as it banks away from you, you would those spaces would be pointing towards you, and you could see in or through the building. That way you could test whether it's leaning away from you. But here again, we're relying on optics. So anyway, you can see the problem of viewing things at a distance, and keep in mind always that the distance measured is along, according to the Ball model, along an arc. It's not a straight line distance. So they can calculate what they think this arc is by assuming certain things like the radius of the Earth. You can calculate this arc, and at what distance, if you're on a tangent line, and let's face it, even 20 feet off the ground would still be insignificant compared to our eyes, compared to the size that they tell us the Earth is. So for all practical purposes, you're on the surface, and they can calculate at what point you should not see this anymore. But it really isn't even, that's an outside limit, because with perspective, with distance, this thing is going to get even smaller, so it will disappear even sooner. But giving them the benefit of a doubt, even in a best case scenario, there are many objects that should be hidden by curvature that are not. And so they invoke optical illusion. Now, granted, perspective is also an optical illusion, but it's something we can at least measure, whereas mirages that the Ball Earth model invokes are much harder to prove. Just because, again, you can theorize and duplicate with a fixed lens, or even a tank with different densities of water, like people put sugar in a tank of water and demonstrate that. You cannot say exactly that those are the conditions prevailing when you look at a distant object and see what you are being told is a mirage. The question is whether you can tell that. And again, we go back to the force the line to settle the issue, because it doesn't depend on optics. It depends on measurement strictly. But I just wanted you to understand that this is a radius. A tangent is a right angle to that, and that's what you see in your line of sight, because normally you're not looking at the ground. You're not looking this way at an object. you're looking straight out. So if it has gone beyond the curve enough to where even, looking straight, you don't see it anymore, it should disappear. And if they invoke optical illusion, then the game is over and the debate is pointless. And also, as I showed in the force the line drawing, here's another illustration of what level means on a ball. That's what level means, equidistant from the surface, and the surface is arcing. Whereas a tangent is a right angle to the radius, and that's not going to change, but that's your line of sight at the horizon. So the horizon is when, the farthest you can see before things drop off. And last but not least, as I have in the words down here at the bottom, and when it comes to people saying the Earth weighs a certain amount, no, it doesn't. It has no weight, because an object's weight is defined as a product of its mass times acceleration. That is the general formula for any kind of weight: mass times acceleration. Okay, any kind of force, I'm sorry. A force equals mass times acceleration. F equals m times a, or ma. Okay, weight is just simply a specific force, that being where you assume the acceleration of gravity on a mass. What results is weight. And all that is, again, is the force that something would hit another object if it were suddenly stopped. That's why when they did that moon supposedly experiment where they drop, an Apollo astronaut has a feather and a hammer and drops them, and because there's no atmosphere, they drop at the same rate. But they don't hit with the same force. That's the thing that it's hard to wrap your mind around sometimes, is they're going to hit with a different amount of force, because this is a force equation. So when we talk about weight, we're talking about the force that a mass is pulled to the surface of the Earth because it's being accelerated by gravity, which is a number they picked. Okay? The problem is, what's the mass of the Earth? Nobody knows. Earth does not even have an average estimated density of mass, since no one knows by observation what lies deeper than about 8 miles below the surface. It's impossible to know the Earth's mass. And since there is no net external gravitational acceleration of the Earth as a whole, Earth cannot have weight. That is to say, there must be an external body pulling the Earth in one direction in order for the Earth to have measurable weight. All it has is mass. Okay, I don't know if that made any sense, but that's as simple as I can put it. So when somebody tries to tell you that they know the weight of the Earth, they don't know what they're talking about, because it's impossible to know, because they can only guess what the Earth's mass is. They can't measure it because they can't drill deep enough. And even if they did, they would have to drill the entire Earth and examine every part of it to know what its mass is. They'd have to put the whole Earth on a scale, and then that scale is presuming gravity, and it's impossible. Okay, look at the chat again. Good to see everybody here. And trusting our eyes. I'm rolling back here, try to catch up on things. Salt flats. Yeah, somebody mentioned Bolivia, and I think that is fakes. That's what I knew it was in South America somewhere, but high up in the mountainous regions, there's the salt flats that are the biggest in the world and very flat for a very long way. That would be also without the humidity and heat, it would be a good place to build that force the line. Let me put that back up here. And like I said, whatever shape the Earth is, you could test it both ways. You could put the tangent here and then put the level, do level above it and do level below it. And you should, if the Earth was concave, the level would go like this. Okay, it doesn't matter. Then you wind up with this football shape and the whole thing, but American football, of course. But the important thing is this vertical post. Everything is attached to that, and you have a tangent that is always at a right angle, not a level, but a right angle. And then you check level to see what shape the Earth is. And if the lines stay absolutely parallel, Earth must be flat. That's the only way you're going to know. Okay, 8-inch diameter scope saw Jupiter's lines. Yes, I can totally believe that. I can even see the lines with my 3.5-inch scope. So 8-inch would be awesome. It just makes it magnified a lot bigger. You can get some more detail. Getting your camera to work in front of the lens on a telescope is a pain. I tried it for years before I got the nifty B900, but you can buy brackets if you don't have one that screws right into the eyepiece on your telescope that will hold a cell phone. I have actually done that. I have a bracket on my scope for my old cell phone. The new one doesn't fit it, but it's hard to line up. It really is, but at least you have to have that kind of a phone camera lens because you're basically putting it right next to another lens, and the average big camera won't be able to do that. You need a special kind of adapter. So let's see. Yeah, I haven't even got into Bible stuff here. I mainly wanted to show that the whole Earth-shaped debate can be settled only, in my opinion, by force the line. All the optical arguments, and that's why I spent most of the time talking about what a mirage is, what a mirage isn't, the difference between the two major types, and what a looming mirage is and isn't, just to dismiss that. You know, we have to be thorough and people have to understand their terms. So if you miss that part, you'll have to go back and watch it. But anyway, let's see. Gravity is a key theory giving credence to globe Earth. I wouldn't necessarily say that because even concave earthers or hollow earthers believe in gravity, that it just goes down into the mass somewhere, even though the other shapes don't have a center, so to speak. There's no guaranteeing that gravity goes to the center of a mass. I think there's too many assumptions in the so-called experiments for that. But my point is, when it comes to Earth shape, I don't care what other else you measure, you've got to measure Earth. And the only way to measure it is force the line, in my opinion. And I did do a video on gravity just not that long ago. It was in the past week. So check out my earlier cosmology videos on, you know, on more on the gravity issue. Let's see. Celestial navigation via nautical sextant and Pythagorean theorem, math, flat math equal flat reality. Okay, and thank you. Yeah, I have a book by a relative of mine who worked with or for the government right around World War II, who wrote a book called Practical Air Navigation. I think that's the title. Was used by the military for a long time to how to use navigation equipment on an airplane. Okay, and all the problems associated with that, and very mathematical, lots of charts and graphs and things. But the point is that way even before that, you know, thousands of years ago, people could cross the ocean. Even before the sextant was invented, as far as we know. So it is possible to have maps and navigation without even knowing what the Earth shape is, just by, and predicting the movement of the sun, moon, and stars doesn't require an Earth shape. It only requires observation and taking careful records of what space bodies do when, and then look for a repeating pattern. That's how you'd predict. You know, you don't need an Earth shape. You don't need any measuring devices except to measure, to make note of the day and time when something happened, when it moved or didn't move, you know, and just keep records. That's how you can predict things. It doesn't depend on Earth shape or technology, just observation. Oh, thank you. I got 2 stars. I'm going to put them up in the sky and make people wonder what they are. Let's see. Modern missile guidance assumed, flat Earth assumed in the missile guidance. Yeah, and again, they would say, oh, that's no big deal that the flat Earth is assumed because the Earth is so big. But that is a circular reasoning. It's an assumption. So I hope it has helped in some way to look at what causes mirages and other optical illusions, why light does what it does, why optics are never going to settle the issue, the debate of Earth shape, no matter which of the several different models people have. You have to build something like this. And as far as sun motion, I've heard people complain about the, flat Earth not having an answer for the sun at equinox. And I'm like, what's the problem? You know, look at my challenging standard cosmology, the sun video. I go into 4 different motions of the sun, tracked it all summer, watch the sunspots. You know, it has an X, Y, Z axis plus a clock rotation every day from every spot on Earth. And all the arcing, north-south arcing cannot be explained by Earth tilt at all, because those are east-west lines, but the north-south arcing is pinching toward the equator. So if you're at the equator, it makes sense that it's going to go straight. I don't care what the model is, what the actual shape is. All I'm doing is watching the sun go overhead. I'm not talking about Earth shape when I do those videos. I'm talking, you know, and I have one on the moon also. I'm just talking about what I see and what other people see in different parts of the world all at the same time. Okay, it presents a problem for every Earth model. And that's why I got into lensing. And that's why I mentioned that that lensing model I had before was from earlier videos, because that's what I think is between the sun and Earth. If you turn this thing sideways, that kind of lensing could explain, say, if you're, you know, in the northern hemisphere is down here, or northern is up here, southern is down here, it could explain a north-south movement as it goes past you over your head. But watch the sun video for that. That's too hard to just imagine right now. So the main thing is today that I wanted to try to explain is what the different types of mirages are, what a looming mirage is, why it happens, and how you can tell whether something is a mirage. You know, just because looking straight at it, you can't always tell, but you can try to look for other things around it to see if they are, you know, at the same height comparative to the object that they would be if you were right next to them, you know, if you're making sure you're close enough not to be looking at a mirage. So you can look at something that you shouldn't be able to see from that distance, according to the ball model, such as something like the red thing over here on the right. And if you see it and they say it's a mirage, then all you have to do is look at things around that building, especially behind it, such as mountains or whatever, and see if the proportions are still the same. If they are, you are not looking at a mirage. Because a mirage would bend the light at different rates from different angles of view, and the farther away they are, the shallower the angle of view, so they're not going to move with the mirage, you know what I'm saying, with the object in front. So that's how you would tell if it's a mirage or not. But you have to double check. And here again, that takes us back to force the line. A physical object does not depend on optics at all. As long as you carefully keep measuring the right angle and the level, you will have your answer. I don't know any better way to do it. So there you are. And I also, in my sun video that I mentioned, go into Earth tilt and also, or, you know, everything to do with that. It's a fairly long video. So that's all I have. If you have any other questions, ask them now, because I'm done with my material that I had. So thanks again for coming. Spread it around if you can, not because, you know, I'm big on getting subscribers, because even if I had 1,000 subscribers, I would not do Super Chat. I don't do that. But it would be nice to get feedback from rational people, the usual trolls. Their feedback is not valuable to anyone. But if you find people who are genuinely open-minded about it, you might want to show them these videos, because I'd be curious what they think. So anyway, thanks again for coming, and we'll see you all another time.